Okay, so let's continue. So we talked a little bit about offered load and throughput, and we finished off by saying that for a MAC layer, there is a specific maximum supported load called rho max. And the implication of this is that the throughput, which is actually what we're trying to give to the different users, is always less or equal to rho max times R. Okay. So obviously, given a fixed R, we would like rho max to be as high as possible, such that the throughput, which is the useful data that goes through the cable or whatever medium we have, is as large as possible. Okay. So going back to this slide and this point, we see that the medium access control can support a normalized load, or load for short, which is less than rho max, which is less than 1, typically. The transfer delay, so remember what that is. The transfer delay is the time it takes from one frame to enter into a MAC layer until it exits out from the receiver MAC layer. That time here, capital T, typically increases as the load increases. Okay. That is, the more busy, the more heavily used the medium is, the longer it takes to get data through that medium. Sort of makes sense, right? And we will see that this is also the case for some practical MAC schemes as we go along. Okay. Something that makes coordination difficult is the delay bandwidth product. And let's see why that is the case. So first of all, what is meant by the delay bandwidth product? So again, we have this type of network where we have a number of stations. All of them are attached to a certain medium. And let's think of this as being a cable now for simplicity. So the first station is attached to the cable here, and the last station is attached to the cable here. And the physical distance in meters between these two things is d meters. Okay. Now the propagation time from here until here obviously depends on the distance and the propagation speed of the medium, right? So the propagation time is d divided by the speed of propagation in the medium. So, some fraction of the speed of light typically. The medium can support r bits per second. Remember that L is the frame length. And let's now introduce a new variable called x, which is L divided by r, and that's the frame duration. This is something that used to be called earlier TF, right? The frame duration. But now in this chapter is called x. The delay bandwidth product, A, is the propagation time divided by L. This is wrong. It should be divided by x. Sorry for that. It's the propagation time divided by x. So it basically tells us, A here tells us how many frames can at the same time be transferred on this cable. So suppose A is popping out frames here. All of them takes x second to pop one out on the cable. How many of these x's can we fit into this cable? That is A. Okay, it's the propagation time divided by x. So if it's 3, it means that 3 frames could physically be on the channel in transit at the same time. If A is 10, we can have 10 frames on the cable in transit at the same time. So, and from this basic definition, it's not difficult to show that A can also be written as R. Since x is L divided by R, we can simply replace x by R divided by L like this. Okay, and we see here that this is some type of delay bandwidth product. We have bandwidth in the computer science nomenclature, it's bit rate, right? Bit rate times some delay Okay, so this is delay bandwidth, and then it's normalized with the length of a frame in bits. Okay, so we will see later on that the delay bandwidth product, which is normalized with the frame length, A here, is a key parameter. A here would simply put, A will determine whether it's difficult or not so difficult to coordinate use of this medium. So coordination efficiency, we will show, decreases when the delay bandwidth product increases. Okay. And we will see shortly an example why this is the case. Questions? Okay. Transfer delay versus load before we go into an example here. So remember that T, the time it takes to transfer a frame, is a random variable. It depends on many things. But if you take the expected value of it, it's the average delay it takes to transmit one frame, and divide through by x. And what was x again? Well, x was the frame duration. Okay. So T divided by x is how many frame durations it takes to deliver a frame. And if it's the only frame in the system, it's 1. Okay. So when the load is very low, we have load on this axis, the time it takes to deliver a frame is the time it takes to transmit the frame, which is x. Okay. However, when the load increases, which means that there are more and more users using the network, or more and more frames needs to transmit, this increases and eventually increases quite rapidly when we are approaching the maximum supported load for that medium access control scheme. Okay. So we use the medium more and more efficiently, but the price for efficiency is that we pay with delay. We have to queue more. Okay. This A factor here actually is such that it moves this rho max to the left. Okay. So A is bad in that sense that, I mean, A is typically given to us. It's nothing that we have some engineering capabilities here, but let's think of A as being fixed. Then if A somehow we have a medium where this increases, then we actually go to the left and our maximum supported rate goes down. Okay, which means that we use the medium less efficiently. Okay, so transfer delay, random variable. Frame transmission time is x. L, number of bits in a frame divided by the data rate of the medium. Transfer delay is typically increases dramatically when we are approaching rho max. Okay, remember we can never be to the right here because then we're in an overloaded situation. That could actually be very, very harmful. So we want to avoid that. But anyways, so longer channel access delays is typically the reason for this. And then typically rho max decreases as A increases, where A again is this normalized delay bandwidth product. Questions? Okay. So let's make an example to clear. I mean, we said things very generally now. It's typically like this. These are the things that happens and so forth. But let's go down and do an example to see how all of these things come into play, right? So let's consider a very simple situation. Unfortunately, even the simple situation is a rather complicated protocol here. But for the simple situation, it's the following. We have only two stations, one here and one here. And they're at some distance d. And then we have a propagation time which is proportional to d, obviously, and divided through by the propagation time. Okay, so what we want to do is the follow. This is the protocol. So, that will be illustrated on the next slide. So don't worry if it looks complex now. But anyways, if a station has a frame to transmit, so suppose station number 1 has a frame to transmit, what does it do? Well, first of all, it listens to the medium. That is, it turns on its receiver and see, okay, is there any traffic ongoing on this cable or not? And it listens until it becomes idle, that is free. So either it's free from the beginning or something is ongoing and then it just waits until it's free. So when it's free, when this station cannot hear anything here, what it does then is to transmit a reservation signal to inform all other nodes on the cable that it's intending to transmit. So it waits until it's idle and then transmit a reservation signal, and that reservation signal we will see later on, has to have a certain duration. So it's, in this case, is 2 times the propagation time. At the same time as station number 1 starts to transmit its reservation signal here, which then propagates fast actually, to the right here, but it takes some time before it reaches this destination. At the same time as station 1 starts to transmit it, it also listens to the medium to hear whether maybe there is a reservation signal coming the other way. At this point in time, neither station 1 nor station 2 knows that the other station has transmitted a reservation signal because it has not reached it yet. Okay? So there might be a situation where these two things are initiated at the same time or within a certain time interval when they somehow collide. Okay? Now, so station number 1 starts to transmit this signal, and then it listens to the medium for if there will be another reservation signal colliding with its own reservation signal. If there is no collision, then things are very good. Okay? And then station 1 can, after its reservation signal, just transmit its frame. If there is a collision, however, that means that both stations are intending to transmit. So which one should win? Okay, one needs to win. And the rule here is basically the station that started first wins. And we can actually figure out which station that is. Both stations can figure that one out, actually, as we will see in the example on the timing diagram on the next slide. So if a collision occurs, the stations can figure out which one was the first to transmit, and that one, the first one that started to transmit, captures the medium, it says, or is allowed to use the medium for its frame, and then basically transmits its frame after the reservation signal, and the other station aborts its transmission of reservation signal and just waits. It just lost, right? It has to wait for another turn. And after station number 1 has transmitted its frame, it waits for a certain time to allow station number 2 to potentially capture the medium for the next time. Okay? So the last part here is critical for fairness, as we will see. Okay. Any questions on the protocol before we see the timing diagram? Okay. So here it's a rather complicated diagram, so let's go through this in some detail. Okay. So we have, okay, maybe we should call this station 1 and this station 2, right, to be consistent. So we have 2 stations. And here's a time axis, like this, and here's a time axis. So time is on that, and here we have space, okay, or distance, whatever you would like to call it. Okay, so we can think of this as being actually the cable that goes like this. And if we had the receiver at this point in the cable, it will see the signal along this red axis. That will be the time axis of that receiver. Okay, so what happens here is that station number 1 would like to transmit the frame. So it starts to transmit this blue thing here, which is the reservation signal. So the first bit of the reservation signal is transmitted here, and it goes happily over the channel until it reaches station number 2 at this point in time. Okay. Station number 2 also has a frame to transmit, listens to the channel, it's idle, and starts to transmit its reservation signal that goes over the channel and reaches station number 1 here at some time later on. And of course, the difference between where the first bit is transmitted until it's received is this propagation time. Now, station number 2 has no idea that station number 1 has started to transmit until here. At this point in time, station number 2 sees, okay, I see now that there is another reservation signal on the channel here. Right? So here, what does station number 2 do? Well, it knows that it's not the first one. Why is that? Because it knows that because it has transmitted less than half of the reservation signal at this point in time. Right? So let's see the opposite here. The first bit of the reservation signal for station number 2 reaches station number 1 at this point. But station number 1 then sees, okay, I transmitted more than half my reservation signal, so I know I'm number 1. I'm the first one. So at this point in time, station number 2 knows it's a loser, so it just backs off. At this point in time, station number 1 knows it's a winner, right? But it still has to wait until the last bit of that reservation signal reaches here. Because at this point in time, station number 1 knows, okay, I'm the winner, and now the medium is mine. Right? Station number 2 knows here it lost, so it's not going to interfere. It knows there will be a frame eventually being on the channel. So at this point in time, station number 1 starts to transmit its frame, the green part here, which is the payload, if you like. And it goes over the channel, and then at this point in time, it has reached the receiver. Okay. Station number 1 keeps on transmitting its frame until this point in time, and then it has to wait for at least a propagation time to give station number 2 the chance to start to transmit the reservation signal here. Right? We could think of it that station number 1 started to transmit the new reservation signal here, but then we would starve station number 2, because station number 2 would never get the chance to capture the channel, the medium, until station number 1 has exhausted all its bits. Right? So for fairness reasons, we need to wait a little bit here. Station 1 needs to wait here. Otherwise, station number 2 might never get the chance to transmit. Okay. Questions? Yes?
Yes, like the reservation signal, like that, what is that? Like, just say 1 bit to see if it's like free in the channel, or if we compare it to like our protocol.
Yeah, so what is this in a protocol sense? So we can think of this as a header, right? But rather meaningless header, because it doesn't really carry much more information than something is going on. It cannot be too short, right? It has to be at least 2 propagation times here. Okay, because otherwise the coordination function, who wins the channel, will not function. In this protocol, at least, right? There might be, we will see later on in a more serious protocols that we can do this differently. Right? Good question. Any other question? Yes?
What happens at the boundary? Like, if they arrive at the same time?
Yeah, so that could happen, and then things go badly.
Right. It just goes badly.
Yeah, exactly.
It doesn't get like.
I mean, then the higher layers would, the higher layer ARQ protocol would see, okay, that frame got lost, so I need to retransmit that.
Okay.
So that's a special case which is not covered by this protocol. Any other questions? Yeah. Okay, so it's hard to coordinate, right? Okay, and we see here also, if we would like to calculate the throughput, the maximum throughput of this, what would that be? Well, the maximum throughput is when we go through this cycle, and we have these cycles just adjacent to each other, that we use the medium as much as we possibly can, and then we use the medium then to transmit L bits, but it takes this amount of time to do that. Okay, so the utilization, rather the throughput, the maximum throughput we can hope for is the throughput we can get over one of these cycles, and then these cycles are repeated. Okay, so we transmit L bits. How long does it take to transmit L bits? Well, it takes X seconds to do that, because that's what it takes to transmit the frame. But then we also have some overhead due to this coordination, which is 2 t-prop here and 1 t-prop here. So we have L divided by X plus 3 t-prop. If this would be 0, this coordination time, then we would have L over X, which is then equal to R. Is the best we can hope for. Okay. But anyways, so the efficiency, the maximum load, supportable load, is the maximum throughput divided by R, which is 1 plus 1 over 3A. It's easy to show this. Okay, and this A again is this normalized normalized bandwidth delay product. Okay, delay bandwidth divided by frame length, L in bits. Or if you like, it's the propagation time divided by X. So, So when this propagation time here is long compared to X is when we have problems. Okay? Because then the coordination period is long compared to the frame period where we actually transmit data, and therefore the efficiency is low. Right? And this coordination period, however we do that, is somehow related to the propagation time. Because this is how long it takes to inform each other of what's going on. Whatever station number 1 does takes t-prop seconds to get to station number 2. So that's the problem. So if you ever spoken on a telephone where there is a long delay, you know how awkward that is, because you sort of start to talk and then the other person starts to talk at the same time. You hear that it collides and then you back off and then you start to talk again, right? So it's human communication also have problems with delay bandwidth products. Okay. All right, questions? Okay, so let's start and talk about some serious protocols. And let's start with the simplest possible one can think of. And this is called ALOA. And ALOA here is actually not a acronym. Well, there is some acronym that comes from this. But you can maybe guess where this was invented. On Hawaii, yes. Yeah. So there was this guy, Abramson, at the University of Hawaii who did this. Way back, he liked surfing. I've been told. I don't know the guy, but he liked surfing. That's why he was at Hawaii. And then he had a problem to coordinate data transmissions between the islands of Hawaii, and went over a satellite link, which has a high delay bandwidth product. Okay, so ALOA is very, very simple to stop and wait. So what do? Well, when a new frame arrives, at the station, then the station just transmits that immediately without listening to the channel. Does nothing, just transmit that and start a timeout timer. And then it blocks the upper layers, so which means that if I get a frame from above, I transmit that and then I say, okay, you have to wait until I'm done, just as in stop and wait. And then wait for an acknowledgement. If no acknowledgement arrives before a timeout, then it waits a random time, and we'll see why this is critical in a second, and then transmit the frame again, just as in stop and wait. Just as stop and wait, except that this random back-off time is a new parameter here. And we will see later on why this is critical. If an acknowledgement arrives before the timeout, everything is well, and then we can accept new frames from the upper layer. Okay. So simple enough, I hope. Questions? Okay. So why is back-off needed? Well, here is a situation to illustrate why backoff is needed. So we have in this network 3 stations, and we have again here time, time on this axis, and we have space on this axis, right? So if A gets a frame for transmission here, it starts to transmit that immediately and transmit this frame, and it goes over the medium and actually continues down here also. But then suppose that this frame is then destined for station B here. Then station C also gets a frame here a little bit earlier than station A and transmit the green frame, and there is a collision here. Okay, collisions are bad. Okay, we don't want them. So station B here is completely confused. It doesn't know, it's just noise on the channel. It has a hard time decoding either frames. So we say that these frames are lost. Actually, in practice, there might be situations where one of these frames is actually possible to decode. Okay, but we will ignore that for the time being and say just that we would like to avoid collisions. So if there is a collision here, then station B will not acknowledge neither the green nor the blue frame here. And so A would then, after a timeout, transmit its blue frame again. C would, after a timeout, transmit the green frame again. And what happens? Well, there's another collision, and it keeps on going indefinitely, right? So we're sort of in a locked state here. So this is not what we want to do. So what do we do then? Well, instead of, essentially what we do is that instead of transmitting immediately after the timeout counter has expired, we wait a little bit more. And we wait a random time. So we wait a different time here and a different time here. So we introduce an additional waiting time called the backoff time. So here's the backoff time for A, and here's the backoff time for C. And this backoff times is randomly selected at each time a timeout timer expires. So for B, for A here at this point, A is drawing a random number from its random number generator that specifies how long it should wait. Okay. C, at this point in time, draws another random number from its random number generator and waits another time. And if these random number generators are such that they're long enough, specify a backoff time in a long enough interval, then we can reduce the probability of additional collisions. Right? However, if we choose them to be too long, then we are unnecessarily delaying the transmissions here. So there is always a trade-off. Questions? So this is Aloha. So is it any good? Well, let's analyze that. One can say the following, that Abramson did an analysis that showed what the throughput of this system should be, and the equations that he derived and put forward in his paper gives the right result. However, the analysis itself is flawed. Okay, so it's a situation where the solution is right, but the derivation is wrong. Okay, so if you do that at an exam and there is a lazy PhD student that grades it, he or she would just look at the answer and say, okay, full points, right? While a careful professor would then look at the solution and say, oh, the solution is all wrong, but the answer is right, 0 points, right? Typically the other way around, where the PhD students are more careful than the professors. But anyway, so basically what I will present now is not the right way to analyze this, but it gives the right result, and the analysis gives some insight in what's going on. So it's a justification for the end equation, not the completely rigorous derivation for this. Okay, so to do this, we need to say something about these. If we go back here, to this situation where we have stations here and they generate frames. We say then that they generate frames somehow randomly, right? Not periodically, but in a random fashion. And they generate what's known as a Poisson data traffic. So what is that? Okay. So, Poisson data traffic. So if we take the perspective of station number 1 and look at some time axis for it, at certain times there will be requests from the upper layer to transmit the frame. Okay, so the first request might be here, the second request might be here, the third here, and then the fourth here. Okay, it occurs at some times. Okay, so these are frame transmission requests. The time between these two requests, or adjacent requests, let's call them tau, and let's have an index for them. So this is tau 1. The second inter-request time is tau 2, and the third is tau 3. Okay, so what can we say about these taus here? Then a very common assumption in how to model this is to say that taus are independent random variables and they're exponentially distributed. Okay, so this goes back to queuing theory, where one did studies on people basically standing in line for a post office. You know, how many people are in the queue, and when do they arrive, and so forth. And there's good experimental evidence that that the time between customers arriving is somehow exponentially distributed. You also see this in reliability theory. I mean, how long does a light bulb last? Well, it's typically exponentially distributed. So, anyways, a common model that these tau variables, tau 1, tau 2, etc., all of these are independent random variables, exponentially distributed. With a certain parameter, and the parameter lambda is the also known as the intensity, and 1 over lambda is the average time between these is the average of tau. Okay. Okay, so what does that mean? Well, it means that tau is distributed with a probability density function, which is lambda times an exponential minus lambda u, and this is true for all u greater than 0, and it's 0 otherwise. The average number of events. Okay. So what do I mean by an event? Well, an event is one of these arrivals. So how many of those on the average occurs during a certain time interval is then given by this lambda factor. Okay. Okay, time, and we have to determine some time unit. So lambda is measured in some unit, number of events per second, say, or number of events per year or whatever. Okay. Okay. So this is equal to lambda. Okay, so that means that the average number of events in capital N time units is simply n times lambda. Okay, that was not so difficult perhaps. If it's lambda events per time unit, and if you have capital N time units, it's n times lambda. And if we're interested in the probability density function or probability mass function for how many events that occur per time unit, one can show that what that is also. So in fact, the number of events per time unit. So this is a random variable, and let's call that y. Is a random variable with PMF f subscript capital Y for the random variable y, and then brackets because it's a discrete random variable, it's an integer, and then evaluated at k. So this is by definition the probability that y is equal to k, and one can show that this is equal to lambda raised to the power of k divided by k factorial times the exponential of with the exponent of negative lambda. And this is true for k equals 0, 1, etc. And it's 0 otherwise. Okay, so to summarize, Poisson data traffic means that frames are arriving at a certain random times, and the time between two of these events is an exponential random variable. That's not super important, but it's important to figure out how many of these events occur per second or per time unit. Which is this random variable y. Then it has this probability mass function like this, and the average of that is equal to lambda. And if we extend the time interval to be more than one time unit, then we take n times lambda to get the average of that. Okay. So why is this important? Well, okay, so one property too before we go further here. So if z here is a Poisson random variable with some intensity lambda 2, and y is some other Poisson random variable with intensity lambda 1, then w, which is the sum of y plus z, is also a Poisson. Okay? and the intensity of that is lambda 1 plus lambda 2. So this is almost like this Gaussian property, right? If you have a random variable, random events here and random events here, if you count both of these events, then we get a new Poisson with the intensity, which is the sum of this and this. Okay. All right. Why is this all screwed up? Oh boy. This is not what it looked like earlier. Okay, so let's see. I should try to fill this out. So assumption is that all the, okay, so let's now look at Aloha and try to analyze that. So the assumption is that all the frames have the same duration, x seconds. And during x seconds, a few things can happen, right? So x is our basic time unit here, okay? Then we have some Poisson processes in play. And the number of new frames generated for transmission in the entire network is y, is some Poisson process which is governed by the intensity lambda n. Okay. So think of all the stations here. They have individual Poisson processes generating frames. And if we take the sum of all the frames generated in the network, that is a Poisson process with intensity lambda n for new here. There is a bunch of old frames which are scheduled for transmission also. And these are frames which have been sent over the channel but collided. Okay, so they need to be retransmitted. Let's call them Z. And that's another Poisson process with intensity lambda r for retransmission. Then we say that if y and z are independent, then w, which is the sum of y of z, is a Poisson process with intensity g, where g is lambda n plus lambda r. Okay. So if we think of this as a model of what's going on, here are all the new frames generated by all the stations. Here are all the frames that are held by stations that are in backoff that needs to be retransmitted. So at any given point in time during x seconds, the number of frames which are transmitted is w. Okay, it consists of new frames and old frames which are to be retransmitted. This goes over the channel, okay, and then two things could happen. Either frames goes through, which is success, and then they leave the system, or they collide and then they go back in backoff and enter into this feedback loop. So we sort of have a complicated control system here, where here are the new frames coming in, and they go through the channels, and some of them got lucky and get success, and some of them are fed back like this. Okay. So during x seconds, suppose we want to calculate whether this blue frame gets through or not. The blue frame gets through. I will do this just quickly, and we will do this in more detail next time. Okay. So the idea now is to figure out, okay, whether this blue frame gets through or not, and it takes x seconds to transmit that. It would collide if any other frame is generated over the interval of 2x seconds. This is known as the vulnerable period. Okay. So here one frame was generated, and here one frame was generated, and both of these collide actually with the blue frame. So we can see that wherever a frame, if another frame is generated over 2x seconds, then the blue frame will collide with that, and the blue frame will not go through. Right? So the number of frames generated during these 2x seconds is a Poisson random variable with mean 2g. Why is it 2g? Because it gets g new frames are generated per x seconds. Therefore, on the average, 2g are generated during 2x seconds. Okay. So a particular frame is successful if exactly 0 other frames are generated during this vulnerable period. And this happens with this probability from the PMF that we saw earlier. And so the frames are, there are g frames per x seconds, then the throughput is this. Okay, so that was probably the quickest derivation of ALOA ever done in humankind. So I don't blame you if you didn't follow that, but let's pick this up on Thursday. All right, so see you then.